Point a telescope at a distant spiral galaxy and watch how it turns. The whole thing rotates, slowly, like a vast luminous wheel 100,000 light-years across. Now measure how fast the stars are moving, the ones near the center, and the ones way out at the lonely edge. Newton's gravity makes a very clear prediction about what you should find. Out where the planets orbit our sun, the far ones crawl and the near ones race. Pluto takes 248 years to lap a planet that takes 88 days. Farther out should always mean slower. That is the rule. So the astronomers measured the galaxy, fully expecting the edge stars to be dawdling along. Instead, the outer stars were sprinting, moving just as fast as the ones near the blazing core. Every galaxy they checked told the same impossible story. A galaxy spinning that fast should tear itself apart and fling its stars into the dark. Ours hasn't. Something we cannot see is holding it together, and there is roughly 5 times more of it than everything that glows. This is the dark matter problem. Chapter 1. The spin that shouldn't happen. In the 1970s, an astronomer named Vera Rubin set out to do something almost boring. She wanted to measure, carefully, how fast the gas and stars orbit in the Andromeda galaxy. She expected a curve, speed rising near the center, then falling away toward the rim, the way the planets slow down with distance. A neat declining line that any first-year student could draw. What she found instead has become one of the most famous graphs in astronomy. The speed climbed, and then it just stayed there. Flat. The stars at the very edge were orbiting as fast as the ones near the middle. The line refused to fall. Think about what a flat curve means. For the outer stars to move that quickly without being flung away, there has to be far more mass pulling on them than the glowing stuff can account for. A lot more. And it has to reach out well beyond the visible edge. And it wasn't just the stars. Radio astronomers traced the spin even farther out, using cold hydrogen gas that drifts well beyond the last visible star. Out there, in the apparent emptiness, the curve stayed stubbornly flat. The pull continued where the light had stopped. Either there is a colossal amount of invisible matter wrapped around every galaxy, or our laws of gravity, the ones that land probes on comets, are quietly wrong on the largest scales. Rubin's measurement forced that choice onto everyone, and here is the part that still unsettles me. Rubin wasn't the first to smell the problem. The warning had been sitting in the literature, ignored, for nearly 40 years. Chapter 2. Weighing a Ghost. Back in 1933, a brilliant and famously prickly astronomer named Fritz Zwicky was studying a swarm of galaxies called the Coma Cluster, thousands of galaxies bound together by gravity. Zwicky measured how fast the galaxies were whipping around inside the cluster. They were moving so violently that the cluster's own gravity should never have been able to hold them. It should have evaporated billions of years ago. To keep it from scattering, he calculated, there had to be hundreds of times more mass than the glowing galaxies provided. He called the missing stuff dunkle materiae, dark matter. Then, mostly, the world shrugged and moved on for 4 decades. The reason the idea finally stuck is that the evidence stopped coming from one place. It started arriving from completely independent directions, all pointing at the same invisible thing. The first is light itself, bending. Mass bends space, and bent space bends light. Point a telescope at a distant galaxy, and the light arrives smeared into rings and arcs, warped by whatever it passed on the way. We can map the invisible mass just by how badly it distorts the view behind it. And then there's the smoking gun. 2 galaxy clusters that slammed through each other. The visible gas piled up in the middle, slowed by the collision. But the mass, measured by the bending light, sailed straight on through and out the other side. The glowing matter and the gravity had physically separated. Whatever carried most of the mass barely interacted with anything, not even with itself. It just coasted through a galactic car crash like it wasn't there. The final witness is the oldest light in existence, the faint glow left over from the Big Bang. Its tiny ripples encode a precise recipe for the universe. And the recipe is deeply humbling. Everything you have ever seen or touched, every star, planet, person, and atom, is just 5% of what's out there. 27% is dark matter. The remaining 68% is something even stranger we call dark energy. We are the rounding error. And dark matter isn't just along for the ride. Rewind to the infant universe and it clumps together first, while ordinary matter is still a hot fog. Those invisible clumps become the scaffolding, the gravitational valleys that gas later rolls into to build galaxies. Which means this isn't a footnote we can shrug off. Without dark matter's scaffolding, the gas never collects, the galaxies never form, the stars never ignite, and the planets never have a chance to cool and gather life. No invisible matter, no us. You owe your entire existence to a substance no one has ever held. Chapter 3. The Hunt for Nothing. So if dark matter is real, and there's 5 times more of it than everything we can see, the obvious question is, what is it? And for 90 years, the honest answer has been a confident, well-funded shrug. We know what it isn't. It isn't ordinary matter hiding in dark clumps. We've looked. It isn't black holes in the numbers required. It doesn't shine, absorb, or glow at any wavelength we can detect. It passes through ordinary matter like fog through a fence. For years, the least exotic guess was that it might just be ordinary matter we couldn't see. Burnt-out stars, rogue planets, lone black holes drifting in the halo. So surveys watched millions of stars for the brief brightening that happens when one drifts in front of another. They found a few, nowhere near enough. Not even close to the missing mass. The boring answer was ruled out by the boring, beautiful work of actually looking. Whatever dark matter is, it is almost certainly not ordinary stuff hiding in the dark. The leading suspects split into 2 rival camps. On one side, WIMPs, heavy, sluggish particles left over from the Big Bang. On the other, axions, particles so light and ghostly that trillions could be drifting through your thumbnail right now. To catch one, you go to absurd lengths. You build a tank of liquid xenon, cool it close to absolute zero, and bury it a mile underground to hide from cosmic rays. Then you wait, in the dark, for a single ghostly particle to nudge a single atom. These detectors are now sensitive enough to feel a few atoms nudged in a year. We have built bigger and bigger ones for 3 decades. And the grand total of confirmed dark matter particles caught, to date, is exactly 0. Every few years, a detector reports a faint flicker of a hint. Hopes rise. A bigger experiment looks, and the signal melts away. The search keeps narrowing the hiding places, ruling out suspect after suspect, finding nothing each time. We even tried the opposite approach, not catching dark matter but making it. Smash particles together hard enough at the Large Hadron Collider and, if dark matter exists at the right mass, some should spray out and escape the detector as a telltale slice of missing energy. Physicists added up the energy before and after countless collisions, watching for a gap where momentum had quietly walked off the stage. The books kept balancing. Nothing escaped. After all the smashing, the ledger stayed maddeningly, perfectly complete. Chapter 4. Or is gravity wrong? After 90 years of catching nothing, a fair question gets louder. What if there is no invisible matter at all, and instead, our theory of gravity is simply incomplete out where galaxies live? There's a serious idea called modified gravity that tweaks Newton's law at very low accelerations. And remarkably, it nails those flat galaxy rotation curves with a single elegant adjustment. No invisible matter required. But here is where the bullet cluster comes back to bite. In that cosmic collision, the gravity and the glowing matter ended up in different places. Modified gravity can't explain that. If gravity just follows the visible stuff, the two should never have separated, so we are left balanced on an uncomfortable ridge. Dark matter explains the colliding clusters but can't be caught. Modified gravity can be caught on paper but fails the collision. Neither side can claim the win. Most physicists lean toward dark matter because more independent measurements line up behind it. The lensing, the clusters, the ancient light, the very pattern of the galaxies all agree. Modified gravity can match one of those at a time, but never all of them at once. Still, leaning toward an answer you've never once held in your hand is not the same as knowing it. And there's a humbling possibility nobody can rule out. That dark matter is real, but made of something so far outside our particle physics that none of our detectors are even built to feel it. We could be fishing the right ocean with entirely the wrong net. Step back and the scale of it lands. 85% of the matter in your own galaxy is a substance we have never seen, never caught, and cannot name. It is holding your night sky together right now. We can weigh it, we can map it, we can watch it bend starlight and carry whole galaxies through collisions. We just cannot, after 90 years of trying, tell you what it actually is. The most common matter in the universe is still, essentially, a rumor we cannot stop believing, because every instrument we point at the sky insists, again and again, that it really is out there. Most of the universe is missing, and we only know because of how hard it pulls. If puzzles this big still sit unsolved over our heads every night, the channel is full of